Hello everybody and welcome to this Loughborough University Mathematics Education Network video. My name's Laura Alcock. I'm a reader in the Mathematics Education Centre here at Loughborough, and I'm going to talk to you today about self-explanation training and in particular around the transition to undergraduate mathematics. So this video will obviously interest primarily teachers who teach students who might be thinking about going on to undergraduate mathematics, but I think it will also interest more people because it's really about how people make sense of written mathematical information. And that, of course, is important throughout education. So I'm going to start with a little bit of background. So that's what I look like roughly. Like many of you, I was an undergraduate in mathematics. So I did a BSc and then an MSc in mathematics. I then moved across and did a PhD in mathematics education, where I studied students' learning of real analysis at undergraduate level, something I've come back to ever since. I then spent 4 years at Rutgers University in the USA, where I had a joint appointment in mathematics and education. Then 2 years at Essex as a teaching fellow in mathematics, so I just taught mathematics during that time. And then I've been for 14 years here in the Mathematics Education Centre, where I conduct research in undergraduate mathematics education, although that does spread out a little to things on experts and people just below that level. And I have taught some education courses, but primarily I've been teaching undergraduate mathematics during that time. You might know my name from some books. So these are all books that I've written. Rebooted is more of a popular maths book, but the others are all research-based guides for undergraduate students, either general or in specific topics. You may have come across those. So just a quick overview of this talk. Undergraduate mathematics students see a lot of proofs. They see them written down in lecture notes, they copy them down, they see them in books and so on. But how much do they learn from them? Perhaps you remember your early undergraduate experience. Maybe you didn't get as much out of what you were learning from proofs as you might have done. That's certainly common. Certainly that was the case for me. This talk is about our use of psychological research methods to generate and analyse empirical evidence on mathematical reading, so on how people make sense of written mathematics like proofs. I'm going to do that in 2 stages. First of all, talking about eye movement analyses of expert and novice reading. And second, talking about self-explanation training as a student-focused intervention to help people read more effectively. So first of all, on expert and novice reading, this is work I did with Matthew Ingalls, a long-time friend and colleague here at Loughborough. And what I'm going to do first is I'm going to show you a proof which may or may not be valid. This is one that we used in one of our studies, and I would like you to have a look at it so you get a sense of what it felt like to be trying to make sense of that and making that judgment. What I'll do is I'll put it on the screen and then I will pause, invite you to pause the video so you can look at it for as long as you think is necessary, and then I'll start again. So here is the proof. You may want to pause the video now. And I will carry on. So hopefully you've thought about that, thought about what your judgment would be. As I said, we used this in a research study. This one involved 12 mathematicians and 18 undergraduates. They were shown that proof, but also 5 more, so 6 purported proofs. 4 were short, like that one, and presented as produced by students, so there was some doubt about whether they were valid or not. And 2 were longer and presented as sent to a recreational mathematics journal. So once again, we wouldn't expect them to be perfect. So people were asked to read each one, decide whether it was valid, and rate their confidence in their own judgment. And just so that you know, as we go forward, on the validity issue, all 12 mathematician participants said that the preceding proof was invalid. They all agreed about that. But of the 18 student participants, 9 said it was valid and 9 said it was invalid. So the students really didn't agree, and in particular, a lot of them didn't agree with the mathematician's judgment, which does indicate something about how well students are able to process this information. That's broadly in line with other research with similar populations of undergraduates, that they're not very reliable about validity judgments. And we're going to think about why. But the interesting thing for our study was not just the judgments, but indeed what people were doing while they made those judgments. So what you're seeing on the screen now is a picture of our eye tracker that we used at the time. We have a new one now. It just looks like an ordinary computer screen, but it has these infrared emitting diodes which are able to sort of look into the person's eyes and track where they're reading on the screen. This is what it looks like when that has been recorded. I'll just show you that. You can see this person is reading from left to right, top to the bottom, and they're reading the instructions of this experiment that I'm talking about now. So eye tracking is used in study and reading. As I said, it uses infrared, non-invasive methods for doing this, so the person doesn't feel anything at all. The tracker has to be calibrated when a new person sits down to do a study, but after that, what that involves, is them following a dot around the screen to check that the tracker is able to follow them okay. But after that, the screen behaves as normal, so it just looks like a normal computer screen. They don't see any of those dots you just saw. It's used widely in research on reading for obvious reasons. And the dots you just saw are fixations. So although when you're reading static images, you might have the impression that your eyes are sliding smoothly across the page. In fact, they're not. When people do read across screens like that, they make fixations lasting around 150 to 500 milliseconds. And those are interspersed with rapid saccades during which no information is processed. It's well known that fixation and attention are closely linked. And this allows us to study things like the comparisons of differences between experts and novices in their eye movements. So the questions I'm going to address in just the next few minutes are about this reading of these 6 purported proofs. First of all, do experts and novices fixate differently on algebraic symbols and on logic as expressed in words? There have been some claims that they do. And second, do experts and novices show patterns of saccades consistent with searching for implicit warrants? You might already have an idea of what I mean by that, but I will be explaining as we go on. So first of all, fixations. This image that you're seeing now, this is one of the longer proofs from our study, and what you're seeing is a heat map which shows where the undergraduates on average looked. It's read in the obvious way, so the sort of hotter, the redder the colours, the more the students focused in those areas. And you can see it does look like they're focusing more on the algebraic parts than on the words in that proof. The next screen shows the same one where the mathematicians looked. So clearly there's a difference, right? Students, mathematicians. And in particular, the mathematicians seem very interested in that big long line in the middle of the proof there. And that's because that line is not in fact valid. It has a claim in it that's not true in general and is not justified by anything elsewhere in the proof. So that's not valid, and the mathematicians clearly noticed that. The students, not so much. And of course, so these images provide us with some clear sense that something is going on, but really we want the statistical information to look at that properly. So here is a graph showing the mean total dwell time on formulae and non-formulae for mathematicians and undergraduates. So mathematicians on the left, undergraduates on the right. The dwell time is the total of all the fixations in particular areas. So fixations on formulae and non-formulae there. The error bars, these things here, show plus or minus 1 standard error of the mean. That's the same throughout this talk. If you don't know what that means, you won't miss anything. But what that means basically is these are the results from our study. But what we're really interested in, of course, is how good an estimate is that likely to be of how mathematicians and students behave in general. So that's somewhat that the error bars give an indication of that. And an ANOVA, so a statistical test, revealed there a significant type by status interaction. What that means is that the formulae, non-formulae looking was different if you were a mathematician or an undergraduate. So on the statistical information there, P equals 0.006 means that the probability of that happening, getting a difference that big, if there was nothing really going on in the larger population, would be very low. Typical cutoffs for thinking something is significant are 5%, so 0.05, so this is very low, so there's really something here. You can see that students spent proportionately longer, so more of their time fixating on the formulae than did the mathematicians, but actually that's not really where the action is. So the mathematicians and the undergraduates spent about the same amount of time on the formulae, and the difference is that mathematicians spent proportionately longer focusing on the words. What about saccades as people moved through the proof? So saccade patterns are it's not obvious how to analyse them because a 5-minute read could contain 1,000 fixations. So global comparisons tend to be quite impractical. So what we did was we looked at between line saccades, so saccades from one line of the proof to another, rather than say just along the same line or off to white space. And we can watch somebody making some saccades like that as they read this proof. Notice how different this is from just reading the experiment instructions. You might also notice that some of the circles get bigger. Those are longer fixations. completely different, right? It's completely different from ordinary reading. This is a mathematician reading this. The mathematical reading is very different from what you would see in an ordinary reading of ordinary text. And that is reflected in the statistics once again. So what you're looking at in this graph is the mean number of between line saccades per proof. So how many jumps from one line to another did people make? And you can see there that there is a lot of one distance jumps, so jumps from one line to the next or the previous line, somewhat fewer larger jumps, and that the mathematicians made more jumps. So again, there was a type by status interaction, so that it was different if you were a mathematician or a student. And this time the big difference was in single line jumps, so jumps from one line before or after to the one before or after, where the mathematicians made significantly more of those. I actually was a little bit surprised by that. I thought the mathematicians might make more bigger jumps, but they did seem to go up and down a line at a time. So what does that tell us? Well, I think that finding is particularly notable given the content of the proofs. They were suitable, they had to be, for our study, for undergraduates to understand, so they were all in fairly basic number theory. That means that the content would have been straightforward for the mathematicians. So this back and forth reading seems to be a real signature of expert mathematical reading, because if anything, because it was easier, you'd expect the mathematicians to have to do that less. You would expect the students to have to do more work in that way. So the fact that the mathematicians did more seems to indicate they're really doing something that is associated with expertise. Just to follow up on that, in particular, we looked at warrant-seeking moves, where what I mean by that is that if you think of a proof as a sequence of deductions, so we go from a premise at the beginning or one or more premises, we make various deductions until we arrive at the conclusion that we want. Someone seeking a warrant or a justification for line n would be expected to move from line n to line n-1 and back again. So sometimes in a proof, we might say, okay, this line is justified by this particular result, but quite often those are left implicit and the reader has to sort of work it out if the author thinks that there's something fairly obvious in how that deduction is made. It's also worth noting that some statements don't require warrants. So for instance, we might introduce notation, say let n be a member of the natural numbers or something like that, and we were able to use that without having to justify it. That can be done at any time. So most lines require some kind of justification, but not all of them. And we looked in particular at these warrant-seeking moves in relation to warrant-requiring lines and ones that did not require a warrant. And you can see the difference there on the graph. So that's the mean number of warrant-seeking sequences made by mathematicians and undergraduates. And again, there was a significant type by status interaction, so the differences were different if you were a mathematician or an undergraduate. The students did seem to notice when a warrant was required, they made those kinds of moves more often when some kind of justification was required, but not as much as the mathematicians did. So the mathematicians seemed to do this more than students. They seemed more interested in looking backwards and forwards in a manner consistent with thinking about justifications or warrants, as we're calling them here. So that sort of wraps up that kind of study. We've seen some differences in mathematicians and students' reading. And what we became interested in there was whether we could help students improve their reading. And the approach to that we took was using self-explanation training. And this is work that was done by Mark Hodds, who was a PhD student working with me and Matthew. So we were interested in this, could we teach more effective reading? Because we thought if undergraduates do know when to seek warrants, but just don't do it as much as mathematicians, perhaps that we can teach them to read more effectively. Perhaps we can teach them to look better and understand proofs better in that way. So what we did was we adapted some self-explanation training. This was based on early observations that more effective learners from text on Newtonian mechanics made more self-explanations as they were reading. But variations on it have been shown to be effective in various subjects, including in lower level mathematics before we began. So we were interested in sort of proofreading in undergraduates in particular, but self-explanation training is something that is widely used. And this is the self-explanation training that Mark adapted. So I'm going to read this one for you, how to self-explain. To improve your understanding of a proof, there is a series of techniques you should apply. After reading each line, try to identify and elaborate the main ideas in the proof. Attempt to explain each line in terms of previous ideas. These may be ideas from the information in the proof, ideas from previous theorems or proofs, or ideas from your own prior knowledge of the topic area. Consider any questions that arise if new information contradicts your current understanding. Before proceeding to the next line of the proof, you should ask yourself the following. Do I understand the ideas used in that line? Do I understand why those ideas have been used? How do those ideas link to other ideas in the proof, other theorems, or prior knowledge that I may have? Does the self-explanation I've generated help to answer the questions that I'm asking? So that's the first slide, the first sort of section. The second provides a theorem and some sample self-explanations. What I'm going to do is suggest that you pause the video here to read through this theorem and proof and the possible self-explanations. I will continue. I hope you've read that. So you'll see that's some demonstration of what self-explanation might look like. The next bit I'm going to go through again explains about self-explanations compared with other comments. And it said, you must also be aware that the self-explanation strategy is not the same as monitoring or paraphrasing. These two methods will not help your learning to the same extent as self-explanation. Paraphrasing. A, B, and C have to be positive or negative, even whole numbers. There is no self-explanation in this statement. No additional information is added or linked. The reader merely uses different words to describe what is already represented in the text by the words even integers. You should avoid using such paraphrasing during your own proof comprehension. Paraphrasing will not improve your understanding of the text as much as self-explanation will. And then there's an explanation of monitoring. Okay, I understand that 2 times k plus l plus p is an even integer. This statement simply shows the reader's thought process. It's not the same as self-explanation because the student does not relate the sentence to additional information in the text or to prior knowledge. Please concentrate on self-explanation rather than monitoring. A possible self-explanation of the same sentence would be, okay, 2 times k plus l plus p is an even integer because the sum of 3 integers is an integer and 2 times an integer is an even integer. In this example, the reader identifies and elaborates the main ideas in the text. They use information that has already been presented to understand the logic of the proof. So that's basically what the self-explanation training amounts to. The training that we provided then had a couple of short sample proofs for students to practice their self-explaining with. Just a little bit, this is not a theory heavy talk, but a little bit, why should self-explanation training work? Many of you may well have seen this sort of model of how memory works in general. So there is perception, we perceive something in the world. We have our working memory, which is where all the thinking we experience as thinking takes place. So processing takes place there. And what we will end up doing is some kind of behavior in response to that. What learning means in this sort of model really is getting things into long-term memory. So using our working memory in such a way that we can store information in long-term memory and then retrieve it. Because things can only be processed in working memory, but working memory has a very limited capacity. Long-term memory has a much larger capacity. So self-explanation training works by making more higher quality links between new information and the existing information in long-term memory, and helps with retrieval because more higher quality links make relevant information less likely to be muddled and easier to retrieve. So that's a bit of the theory behind why this should work, and indeed has been shown to work in other studies. We, of course, were interested in, would this change students' reading of purported proofs? So what Mark did first was a lab study. 76 undergraduates volunteered to participate in this study. They were split into self-explanation and control groups by this design. So they were randomized into groups as they came to the experiment. They came one at a time. The self-explanation people received self-explanation training. The others did a control activity where they read something on the history of mathematics, just so they would kind of be in the experiment room for the same amount of time, roughly. Everybody then read proof A. Everyone was then asked to explain the proof line by line. The only difference there being that the self-explanation group were asked to use the self-explanation training in order to guide how they did that. And then everybody did a comprehension test. These were all done individually in the lab, as I say. So we have 2 outcomes there. One is the quality of the explanations that people provided at that stage. And the second is the test score. So how did they do on a comprehension test we had designed for that proof? And now this graph shows a lot of information. This is the types of explanations that people provided. Oops, sorry. So you'll see down the left, there were explanations that were explicitly about inferring warrants. So saying why was something justified. Noticing coherence. So noticing how things link together across the proof. Goal-driven explanations are ones that are sort of explaining why we would want to do something, like what that was aiming towards. The others are a little more obvious: no comment, false, paraphrasing, negative monitoring, or positive monitoring. Above this green line is basically the good stuff. And you will see that there are significantly more high quality explanations from the self-explanation group. Indeed, about twice as many of each of the good kinds of more in-depth explanation. And that was statistically significant in each case. So the self-explanation training does seem to have made a difference to how students can self-explain. And indeed, it does seem that they can do it, right? So they do make more of these higher quality explanations. And then for the comprehension test, this is the mean scores. We've split these by year group. So the students were volunteers, but they came from all three of the undergraduate years, year 1, year 2, year 3. And we were interested in, maybe it doesn't make a difference for some group, but does for others. To analyse this, we used an Ancover with time as a covariate. So this is about the difference between means. And we wanted to factor out how long things took, because we weren't really interested just in, did the self-explanation training make people read for longer? If it did, that's probably not a bad thing. But really, we're interested more in, did they learn more per minute, if you want to think of it that way? And indeed, so with that factored out, there was a significant effective condition, whether they had self-explanation training or not. And there was a main effective year. So those in year 3 did outperform those in the other years. But there was no year by condition interaction, meaning that the self-explanation training had a similar effect across all 3 years. You can see from the graph, not exactly the same, but there's no statistical evidence for it being more different in some cases than others. So that did mean that it seemed to make a difference right the way through people's undergraduate time. So that did seem to work in the lab study. We did seem to get better quality explanations, and we did seem to get better proof comprehension as a consequence. Having done our eye movement study before, though, we were interested in, could you see it? Could you see this happening in the way that people read? So Mark conducted a further study using eye movement methods. This time we had 32 undergraduate participants. The data from 28 was used. Eye tracking, as you might imagine, is a bit vulnerable to certain kinds of things not going quite right, even after calibration. So if somebody has got particularly dark eyebrows or is wearing a lot of makeup, the eye tracker finds it a bit more difficult, for instance. And sometimes hair gets in the way and things like that. So generally speaking, there's more of the data has to be kind of rejected because we didn't get adequate tracking. But still, 28 participants is actually quite large for an eye tracking study. And this is the study design. So this is a little more complicated. What you have there is randomization into groups again, where the top 2 were self-explanation and the bottom 2 were the control groups. And I'll just explain why it's so complicated. You can see that everybody read a proof and did a comprehension test, then had the training or the other activity, and then read another proof and did another comprehension test. So the reason that we had a proof before and after the training was that individual differences in eye movements can be quite large. So the way you will read and the way I read might naturally be a little bit different. And we were interested, therefore, not in the absolute sort of measures for eye movements after the training, but in how they related to what a person would normally do, had it changed what they would normally do. So we needed a measure beforehand. And then the reason that we had 2 groups within that is that for all we knew, a proof might change the way people read as well. So it could be, if it looked like people behaved differently on proof 2, say, when they'd read proof 1 before the self-explanation training, that could be because of the training, or it could be because the proof itself was different in some way that prompted different eye movements. So that's why we have a counterbalance design with some people getting one before and some people getting the other before. And this is what happened. So this is the mean number of between line transitions, what we were interested in this looking backwards and forwards kind of behaviour. And it's pretty obvious what's happening there, so I'll explain the statistics nevertheless. This time we used an Ancover with 2 covariates. So the overall duration of the second reading attempt, because again, we were interested not just in whether the training made people read for longer, but whether they learned more per reading time. We also factored out the number of between line saccades during the first proofreading attempt, so that we were looking at changes in proofreading behaviour, not just their absolute numbers of between line transitions at the end. Of course, the graph just showed the total numbers. You can't really show the Ancover on a graph. This did reveal a significant effective condition, so it mattered whether you were in the self-explanation group or the control group. And a significant effective proof order. So it mattered which proof you saw second. You can see there that proof 2 just prompted a lot more between line transitions anyway. If you're interested, proof 2 was a proof by cases. So it had 2 cases that fit together in order to prove the overall result. And that seems to account for that. Importantly here, there was no significant interaction between condition and proof order. So self-explanation training made a difference no matter which proof you saw second. And you can see that in here. So the self-explanation group did more of these moves regardless of which proof they saw second. And the proof itself did make a difference, as I just said. So it mattered which proof that you saw, the types of behaviour in your eye movements that you made. So that did seem to make a difference there. So we've seen that people did behave differently after they'd had self-explanation training. The final thing I'll talk about is a classroom study, which as teachers, I'm sure you will care about. So, and I am a classroom teacher more often than I'm a researcher, right? So I'm interested in things that work not just in the lab, but outside of the lab as well. I am interested in things that work in the lab because a controlled study in a lab can allow us to really look properly at things that is very difficult to look at in the classroom. But then, of course, we would expect effects in the lab perhaps to be slightly larger than they might be in the messier context of the classroom. So we were interested in that too. So in this case, we had 107 calculus students take part. So these were people taking a first-year undergraduate calculus course. They were in an ordinary lecture theatre. They were randomised into self-explanation and control groups just by whatever was the last digit in their student number, whether that was odd or even. They were asked to sit on different sides of the room depending on that. The control group had some reading on time management as an undergraduate this time. And what everybody did was they had their reading, then they read a proof, did a comprehension test. We then had 20 days delay because we were interested not just in whether they would learn more from something at the time, but whether the effect would stick. And then they read a second proof and did the comprehension test. And just to make sure everyone saw everything, they then read whichever of the self-explanation training and the time management they had left, whichever one they'd left over. And this time the graph's a bit less exciting. So this was a comprehension test out of 10. The self-explanation group in yellow, the control group in red. This graph shows the mean scores at post-test and at delayed post-test. And an ANOVA showed a main effective condition, so it mattered which group you were in. Self-explanation group scored higher. And importantly, it showed no significant interaction of effect of time. So the effect stuck from the immediate to the delayed post-test. And no interaction between condition and time. So it's not like there was more drop-off for one group than the other in that case. So that did work in the lecture theatre as well. The self-explanation groups did better and over time. So here's a little summary of all of that information. We saw that mathematicians attend more than students to the words in the proofs. Sorry, there's an extra more in that sentence. That was sort of predicted. It has been suggested before that students might focus quite a lot on the algebra and whether that's right, but perhaps not read where all the logic really takes place in a proof, and that did seem to be the case in our data. They tend to shift their attention back and forth more in a manner consistent with seeking warrants. So mathematicians behave in this way that's a little bit different. There does seem to be some expertise in the way mathematicians read. It's not just that they read more, they read in a different way. And we saw that in the little movie of the eye movements there. The self-explanation training that Mark Hodds developed or adapted from existing training leads students to give better quality explanations, leads to higher scores on proof comprehension tests, and generally leads to reading behaviour more like that of mathematicians. So the students who'd had the training were prompted to read in such a way that they were apparently trying to make more links across the proof as they read. So what does that mean? Well, here's a bit of discussion. I like talking about these results because they're positive. A lot of results in education, a lot of research in education ends up being rather negative, ends up being about what students can't do, certainly in maths education, conceptual problems, all those kinds of things. But here is something that's positive, something that we can make better with relatively little input. As I say, they're about what students can do, these results. Self-explanation training is short, it's generic, and it's focused on developing student skills. So students can give better explanations if they're given appropriate guidance. They can give better explanations to themselves in a way that results in better learning. It's not a silver bullet, right? So this doesn't solve all the problems or make them understand everything or turn them into readers who are exactly like mathematicians, but the evidence is strong that it does make study more effective for this type of mathematics. And I would say that perhaps versions of it can help teachers to introduce and structure reading activities in mathematics. I think that would be worthwhile. As someone who works a lot with undergraduate mathematics students, I think that a lot of them come very well prepared in some respects, but somewhat less prepared in other respects. And one way in which they're often less prepared is that they haven't learned a great deal by reading. That's fair enough. That's not really how school education works a lot of the time. But when they come to university, they are going to have to do more independent reading. They're going to understand less during lectures, so they're going to need to read more afterwards in order to understand what they've been shown, maybe to look up things in books elsewhere if their lecturer's explanation doesn't quite make sense to them. So these are very worthwhile skills to develop for mathematics degrees. I would say also for just being a citizen, being able to process somewhat complicated quantitative information is obviously a useful skill. And it's, from my position, it's something I would like to see students become. I'd like to see them arrive already feeling more confident in that. So that is my final word. I'll just note that these are some research papers that describe the content that I have talked about today. You might want to start with this last one if you're interested in reading. This is less of a journal paper and more of a magazine article that covers the results, as I have done here, in a fairly brief way. It points you to the more detailed descriptions in the previous two articles too. These, I just want to acknowledge some people who provided funding for the various research reported here. These are my books. The red one and the green one both contain the self-explanation training in slightly different versions because of the different subjects. And with that, I will say thank you. Thank you once again to Colin Foster for the opportunity to present one of these Lumen talks, and I hope that you enjoyed it. Goodbye.